So our next speaker will be online, Stefanie from U Ottawa. She'll tell us about some Monte Carlo's transformers. Yes, please get started.
Okay, yeah, thanks a lot for the kind introduction. And yeah, thank you also very much for the invitation. It's a great pleasure to be part of QSIM, and I'm very sorry I couldn't make it in person. I would have preferred to be in the room with you now, but it didn't work out. So here we are. I have to give my talk online, and I will talk about variational Monte Carlo with large patched transformers. And don't worry, I'm not talking about any electronic components here, but rather about how we can model ground states of quantum many-body systems using artificial neural networks. And transformers are one special kind of artificial neural networks that probably every one of us is using daily right now. Transformers are very powerful for natural language processing. And examples where we use transformers are the DeepL translator, which is a very powerful tool to translate text from any language into any other language, basically. Grammarly is another nice example, which helps us to find typos or also grammar errors in texts that we write, or also suggests to reformulate texts so they sound better. And of course, the most famous example is ChatGPT, which I think I don't have to explain here, so everyone should be familiar with this. And the reason why all these models are so powerful is because they are based on these transformers, which are really strong in dealing with long-range correlations. And this is the reason why in all these tools, we can use long text. So we can apply, or we can translate, or also have checked long text using these artificial neural networks. And this is because transformers are so good at dealing with sequential data. Another example where transformers are used is image generation or image processing. And this is the same principle. So here we have an image is a sequence of pixels, and we have a long sequence of pixels, which are strongly correlated. And transformers are so powerful in dealing with these long-range correlations in sequences that they can do really impressive things with images. So for example, they can generate images just out of some text that we give it. They can draw an image around a smaller image, which still looks very, very realistic. They can add elements into images if we ask them for. And this is all, it really looks very realistic, and it's very impressive how transformers can deal with this data. And so based on all these experiences, quantum physicists are wondering, well, can we also make use of these impressive powers of transformers in quantum many-body physics? And during the last couple of years, several groups looked into how transformers can be applied in quantum many-body physics. So for example, for quantum state tomography, where people reconstruct quantum states from a finite amount of experimental measurements. Or here in these examples, people use transformers for Hamiltonian norming, or also generalizing to different Hamiltonian parameters to describe a system. And another example of applications that I will focus on today is to do variational Monte Carlo. So basically variationally find ground states of a given Hamiltonian using these transformer models. And I will show you today how this can be done, and also how we modified the transformer architecture such that we get a really powerful variational algorithm to find ground states. And before I tell you more about how these neural networks work and how the transformers work and what we do with them, let me introduce the quantum system that I will use as a toy model here to benchmark all our numerical methods. And here I will look at Rydberg atom arrays. So Rydberg atoms are neutral atoms that can be prepared in two different states. So we have ground state, or a highly excited, or so-called Rydberg state. And then we arrange these atoms on lattices, where we always focus on just a two-dimensional square lattice. And via projective measurements, we can read out the information of each atom, whether it is in the ground or in the Rydberg state. The system is then described by the so-called Rydberg Hamiltonian, which consists of three terms. So the first two terms are generated by an external laser driving, and they affect each atom individually and create a detuning of the excited energy level by a factor delta, and also a Rabi oscillation between the ground and the Rydberg state with the frequency omega. And then we have an interaction term here, which is an all-to-all interaction between the atoms. And this can be described using the van der Waals interaction. And the most straightforward way to imagine this interaction term is that if we think about one atom being in the excited state, then we know that it's a highly excited state, meaning that the electron is on a sphere with a very large radius and comes pretty close to all the neighboring atoms. And this is where it causes these van der Waals interactions. And this interaction behavior causes what we call the Rydberg blockade, which basically means that if we have an excited atom, then within the Rydberg radius, or this radius RB, any other excitation would be penalized. Okay, so this is the blockade mechanism that no other atom can be excited or in the excited state within this Rydberg radius. And the reason why we look at these systems is that on the one hand, numerical methods or numerical studies have shown that by tuning these Hamiltonian parameters, we can prepare the system in a huge variety of different phases of matter, which are separated by different kinds of quantum phase transitions. So already from the theoretical side, there's a lot to study and to explore in these Rydberg atom arrays. At the same time, people are realizing these Rydberg atom arrays experimentally, and they have shown that they can very accurately and very efficiently arrange all these atoms on two-dimensional, even three-dimensional lattices. And by tuning the Hamiltonian parameters, they can really prepare these phases that have been predicted theoretically before. And so all this together makes Rydberg atom arrays very promising candidates for high quality quantum computation and quantum simulation, which is why we really want to understand these systems better. Another nice property of the Rydberg Hamiltonian is that it is what we call stochastic, which basically means that we can mathematically prove that the ground states of the Rydberg Hamiltonian are always positive and real valued. And so if we want to look only at the ground states, we don't need to care about complex phases. We don't need to worry about all this, but all information is covered in the squared wave function amplitude. And you will see later that this makes everything a lot easier when we use our neural networks to find ground states of this Hamiltonian. And at the same time, this property allows us to do quantum Monte Carlo simulations of our Rydberg atom arrays, which we can use as a benchmark for our neural network methods later. Okay. So now we all know that if we look at qubit systems, then we can never study them exactly, at least not at the large scale, which is due to the curse of dimensionality, meaning that our Hilbert space dimension scales exponentially with the system size. And if we would like to study the system exactly, we would need to take all these exponentially many states in our Hilbert space into account, which is unfeasible with our conventional computers. And so we need to find an approximative but accurate description of our qubit systems or our Rydberg atom arrays in our examples. And we can do this by, instead of taking all these exponentially many states into account, we focus on a subset, which we call the physical states. And the physical states are just the ones that describe the dominant behavior of our qubit system. And so if we have the subset of physical states, we have an accurate approximation of our qubit system. So now we have shifted our task from solving an exponentially scaling problem to just finding the subset of physical states. And once we have found it, we can approximately describe our system. And hopefully the subset of physical states scales only polynomially with the system size. And the way we can find the subset of physical states is by looking at the squared wave function amplitude, which defines the probability distribution underlying all our basis states, so just all our possible combinations of each qubit being in the 0 or in the 1 state, right? And so now what we need to do to get an approximative or numerical approximative description of our qubit systems is we first need to find a numerical expression of our squared wave function amplitudes. Once we have found this description, we can sample the physical states from this probability distribution, and this gives us the subset of physical states. Okay, and so while the sampling process is pretty straightforward on a conventional computer, so there exist algorithms that, given a probability distribution, we can generate samples from it. The task is now how do we find this numerical expression of the squared wave function amplitude, and this is where we use our artificial neural networks as a wave function ansatz. And before I talk about transformers, I would like to introduce this neural network quantum state representation using a more basic model, which is kind of a bit easier to illustrate and has been used quite a lot to represent quantum states, which was introduced in these two papers here. And it has also been shown that these so-called recurrent neural networks are really good, or work really well as a wave function ansatz for finding ground states of qubit systems. And so recurrent neural networks deal with sequential data, just as the transformers that I introduced in the beginning. And they always take one element of a sequence as an input, and then they iteratively apply the same RNN or recurrent neural network cell to the given input. Inside this RNN cell, there's a lot of nonlinear transformations going on, and I really don't have time to talk about this in detail. But the important things that you need to know is that inside the RNN cell, we have a number of so-called hidden units, and the nonlinear transformations are defined by variational parameters. And so by tuning this number of hidden units, we can tune the expressivity of the network. So the more hidden units we have, the more degrees of freedom we have. And with this, we have a higher expressivity of our recurrent neural network. The variation parameters are the parameters that we tune when we train the network in order to achieve a target or a desired behavior. Okay. So now if we want to deal with sequential data, the first thing we need to do, looking at our Rydberg atom arrays, is to define a sequence in our square lattice of atoms. And this we just do by snaking through this lattice. So we turn our two-dimensional lattice into a one-dimensional sequence that we then send into the RNN cell one atom at a time. In addition to the state of each or of the single atom, the RNN cell receives as input the state of the hidden units from the previous iteration of the RNN cell. Okay, so we send in the state of the hidden units, and then inside the RNN cell, the hidden units are updated. And by propagating this hidden unit configuration over our sequence of atoms, we kind of generate a memory effect, because these hidden units now cover some information about the state or about previous inputs into the RNN cell, so previous or the state of previous elements in our atoms in our sequence. Okay, so this is how we kind of include correlations between the different atoms when looking at our atom array here. The output of the RNN cell is then turned into a probability distribution over the two possible states of the next atom in the sequence. And from this output distribution, we sample the configuration of the next atom in the sequence, and we autoregressively use it as the input in the next iteration of the RNN cell. Okay. And now, because we are propagating this hidden unit configuration and we are generating this memory effect where we have information captured about the states of previous atoms in the sequence, these output probabilities are probabilities of the state of the next atom in the sequence conditioned on the state of all previous atoms in the sequence. Okay, so this is really where the correlations come in. And so given this setup, we can now define a probability distribution which is encoded in our recurrent neural network, which we just get by taking the product of all conditional output probabilities. And we can interpret this encoded probability distribution as a squared wave function amplitude. And then we can train our network, meaning that we tune or optimize our variation parameters such that we approximate a target squared wave function amplitude, or the squared wave function amplitude of our target state. And now if you want to find ground state representations using our recurrent neural network ansatz, then we can do this by tuning our parameters such that the energy expectation value is minimized, because this is just the definition of the ground state. So how do we get any information about the energy? We make use of the fact that if we sample from the distribution that is encoded in the RNN, or basically we take all these sample states that we get as an output of the RNN, then we can interpret these samples as projective measurements, and we can use them to approximately evaluate expectation value of any observable. And so with this, we can also evaluate the expectation value of the energy. And we then can find a way how to update our variation parameters such that the energy expectation value is minimized, and we find the ground state or a ground state representation of a given Hamiltonian. Okay, so this is the basic idea of neural network quantum states using these recurrent methods, or these dealing with sequential data and representations of our quantum states. And the problem with these recurrent neural networks now is that all the information about the states of previous atoms in the sequence is encoded in this hidden state or hidden unit configuration. Okay, so in order to capture correlations, or any correlations between atoms, we need to encode this information in this hidden unit configuration. And since this has a limited size, we have a limited number of hidden units, our memory cannot be, or it has to be laggy at some point, right? We have to lag some information at some point if our sequence gets too long. So as an example, if we look at just these two atoms down here, they are nearest neighbors in our lattice, but in the sequence that we send into our RNN, they are pretty far apart from each other. So they, like in the physical system, they have a very strong correlation since they are nearest neighbors, but for the RNN, it is really hard to capture this very strong correlation because the atoms are so far apart from each other that information is lost while propagating it through the sequence of RNN cells. And so recurrent neural networks are limited in capturing long-range correlations, and this is where transformers are much better. And so my former student, Kyle Sprague, was very interested in seeing if transformer quantum states can really do better, because transformers are very well known for being powerful in capturing long-range correlations in sequences. I really don't have time to tell you everything about transformers, but in the end, transformers, like transformer quantum states, work very similarly to the RNNs that I just introduced. So we also have this autoregressive behavior. We send, or we define a sequence of atoms. We send in one atom at a time into our transformer model. And as an output, we get a probability distribution of the state of the next qubit or the next atom conditioned on the state of all previous atoms in the sequence. And then we sample the next atom. We use it autoregressively as the input and so on. So this all works very similarly. The only difference is that we don't have a recurrent behavior here, but we have what is called this self-attention mechanism, which I really don't have time to explain this. But the self-attention mechanism always takes all states of all elements in the sequence as an input and provides trained connections to all elements in the sequence. Okay, so now we directly encode the correlations to all elements in the sequence or to all other atoms on our lattice in the network model instead of propagating this information over the sequence. And this is why these transformers are so much stronger at capturing long-range correlations. But apart from this, everything is very similar. So we can really define the same this probability distribution encoded in our transformer now instead of the RNN. And we can train our transformer to approximately describe the squared wave function amplitude of a target quantum state. So again, we can tune or train our transformer to minimize the energy expectation value of a given Hamiltonian to find a ground state representation. Okay. Let's take a look at how these models perform. So now we look at our Rydberg atom arrays with 8x8 and 16x16 atoms. We fix our Hamiltonian parameters to some values where we are close to the phase transition between the disordered and the striated phase. And here we train an RNN in blue and the transformer in orange to find the ground state of this Rydberg Hamiltonian. On the y-axis, you see the energy error, where we compare the energy expectation value that we get out of the state encoded in the network. And we compare it to quantum Monte Carlo simulations, which we use, or which we assume to be exact here, so we use it as an exact solution. On the x-axis, you see the training iterations. So in each training iteration, we update these variation parameters in our network once. And so after enough training iterations, we should converge to a ground state representation. And what you find is that for these 8x8 atoms, both network models converge very well to the ground state. We have a very accurate representation of the ground state after enough training iterations, but the transformer converges much faster. When we look at 16x16 atoms, the transformer still finds a very accurate ground state representation. The RNN doesn't, right? So it still has a pretty large error. And this is again because the RNN is so limited in capturing these long-range correlations. And so overall, we found that transformers do outperform RNNs. So this is kind of what we expected. But of course, this also comes at a cost. And the cost can be seen if we look at the total runtime of these simulations. So you see that the transformer takes much longer than the RNN. And already for these 16x16 atoms, we have a runtime which is almost a week. And so we really cannot go to any larger system sizes. We are pretty much limited to 16x16 atoms, which is not very satisfying. And so my former student Kyle was also not very satisfied with this. And he was very motivated to figure out how we can optimize our transformer architecture to be able to scale to larger system sizes. And here he took some inspiration from what is called the vision transformer. So I told you in the beginning that transformers are also used for image data, image processing. And there we have a similar issue. We have very long sequences because we have a lot of pixels in each image. And this leads to very long computational runtimes. And so what people did in order to optimize these computational runtimes is instead of taking a sequence of single pixels, they take a sequence of patches of the image as an input to the transformer. And this significantly reduces the sequence length. And with this also it reduces the computational runtime. And a similar thing can be done with our atoms. So instead of just looking at a sequence of single atoms, we can look at a sequence of patches of atoms. And we were not the first ones to think about this. So there were a couple of works which already had this idea of using patches of atoms as an input to these recurrent neural networks or also the transformers. And so together with Kyle, we looked into this idea in a little more detail. So as I said, we did this with the RNN and with the transformer model. So instead of sending now a single atom at each iteration into the network, we send a patch of 2 by 2 atoms. And then as an output, we get the probability distribution over all 16 possible states of the next 2 by 2 patch of atoms in the sequence. Okay, so now we have a larger output, and then from this output we sample the next or the state of the next 4 atoms in the sequence, and so on, and then everything else works the same way as for these single atom sequences. Okay, and so with this we have divided the sequence length by 4, from which we expect that our computational runtime is also divided, approximately divided by a factor of 4. And we also expect that, that we find the ground state with higher accuracy, because now we directly encode local correlations in our neural network because we send in a patch of atoms, right? Let's take a look at how this performs. So here we have, in the top row, we have the same plots as I have shown you before. And in the bottom row, we look at the same system. We want to find the same ground state, but we use these patched RNN and patch transformer with 2 by 2 input patches. What you find is that, first of all, the patched RNN does find the ground state for 16 by 16 atoms, which is very impressive and really good. So we already see that we definitely get higher accuracies when finding the ground state. And you also see that the convergence towards the ground state is much faster than in the non-patched approach. Okay. And what is most important, the computational runtimes have been reduced significantly. So overall, this sounds really promising. We find a significant speed up in our computational cost, and we find higher accuracies. And so the next question is, can we not just use larger patches? Because then this would reduce our computational cost even further, would make our sequence even shorter. And well, the accuracies should be at least the same, if not better, right? But now we run into another issue. So we are just shifting the problem around, kind of, because if we increase our patch of atoms, then the output of our network, which is this probability distribution over all possible states of the next patch of atoms, scales exponentially with the patch size. And so here again, we cannot really go to larger input patches, because then our computational cost would again scale exponentially with the patch size. And now what my student Kyle did is he came up with a network architecture, which we called the large patched transformer. And this combines the transformer and an RNN. And so what he did is that he sent a big patch of atoms, so 4 by 4 atoms here, into the transformer. And then instead of just directly looking at the probability of all possible 2 to the 16 states of the next large patch, he sent the output of the transformer into an RNN. And this RNN breaks the large patch down into smaller 2 by 2 patches and samples the state of each 2 by 2 patch one at a time. And from these, in the end, we can build together the state of the next large patch in the sequence. Okay, so this way, the output dimension, the dimension of the output probability distribution is always 2 to the 4. It's always, so we always have these 16 states because we only sample 2 by 2 patches at a time. But our transformer still deals with this large input patch. And the reason why we use a transformer at the bottom followed by an RNN is that this way, while we are dealing with these large patches, we can make use of the powers of the transformer, which is very strong in dealing with these long-range correlations. And then once we deal with these smaller system sizes or these smaller patches, we can make use of the computational efficiency of the RNN. Okay. And so let's add this large patch transformer approach to our collection of results here. So now we added the purple and the brown dots here, which are the large patch transformer with 4x4 or 8x8 input patches, followed by this RNN, which breaks everything down into 2x2 patches. What we find is that the convergence takes a bit longer, so we need some more training iterations. The accuracies are the same, but that's all okay because now our runtimes have been reduced so much that they are totally feasible. So only now on our large patch transformer for the 16x16 atom array only runs for 4.5 hours, which is totally fine. Like it's not a long time, and it suggests that we can definitely go to larger system sizes within reasonable runtimes. Okay, so by using this large patch transformer model, we achieved reasonable runtimes and high accuracies, which is very promising and powerful combination. And so we started to look into how big we can go here. And I'm keeping this rather short now, but yeah, you can look up the details in our paper. So we started to increase the system size. So we went up to systems of 40 by 40 Rydberg atoms. And we looked at, or we tried to find the ground state using different patch sizes or input patch sizes to our large patch transformer. And what you see now is that if we choose a too large input patch size, our accuracy or our energy error gets worse again. And this is because at this point, the RNN, like we reached the limitations of the RNN expressivity again. Because now our patch is pretty large, so we still need to capture pretty long correlations between, or when we use the RNN, when we break everything down in these 2x2 patches. And so we again run into the limited expressivity of our RNN. But if we stay below something like 8x8 input patches, everything works really well. We have very high accuracies, even for these 40 by 40 atoms. And these are system sizes that are beyond everything you can find currently in the literature. And the computational runtime was totally reasonable. Okay. So what we concluded from this is that by choosing patch sizes around 8x8 atoms, we can model enormous system sizes at very high accuracy. So we really find the ground state with very high accuracies, and our computational costs are still pretty low. Okay. And so this brings me to the summary and to the end of my talk. So let me summarize. So by considering patches of atoms instead of single atoms, or a sequence of single atoms when using our neural network quantum states, we can reach higher accuracies, and we also significantly reduce the computational cost, which is always a very powerful and promising thing. Then we introduced this large patch transformer, which combines the transformer and the RNN. And this showed with these, we were able to reach remarkable results beyond state-of-the-art simulations for these Rydberg atom arrays. And now I always talked about Rydberg atom arrays, but technically our approach can be used for any arbitrary qubit system, right? We are not limited to Rydberg atoms here. We just need to exchange the Hamiltonian when we calculate our energy expectation value. And with this, we can look at any qubit system. And the last point is that the transformer models that we chose, even though they seem pretty large, they're actually really small compared to what, for example, ChatGPT is using. And so there's still a lot of potential of increasing the network size and making our model stronger. And this makes it very promising to study quantum many-body systems. And so now we have this really powerful tool, and we're happy to apply it to any systems if you have any ideas, or we can help out with anything in finding ground states of quantum many-body systems. Okay, so let me finish off with thanking my team of students, especially Kyle, who was the driving force in this large patch transformer work, and also my team of students and postdocs here at Ottawa, which is called the Apricot. And with this, I thank you for your attention. I'm happy to take any questions.
So we have some time. We have time for some questions. There.
Oh,
Nice.
I'm getting good at this. So this combination of patching and RNNs. So I guess in DALL-E, don't they also patch because images are actually still pretty large, right? And did they also use?
I'm pretty sure they are patching too. Yeah.
Yeah. Do they also use RNNs? Like how is your approach different from what is done in DALL-E or in vision problems?
So, yeah, like I don't know exactly what is done in DALL-E, but I think what is new in our work is definitely this using this RNN to break down the patches into smaller patches so that our output dimension does not scale exponentially. So while this patching approach is definitely, like as I said, it's inspired from this vision transformer, which is used for images. But breaking things down into smaller patches after the transformer using this RNN is what we really introduced here.
So they didn't have the same problem with needing to do that with image data? Like this is you would really want to do this only with quantum problems, is that?
No, yeah, their output would also scale exponentially, obviously, with the patch size. But yeah, I cannot tell you how they solved this issue. Like I don't know the details behind DALL-E. I know there's some hierarchy approach how to reduce this output dimension. But we found that this RNN approach is actually much more flexible and more general than this hierarchy. And also, I think it was computationally cheaper.
All right, thanks.
Other questions? Okay, if there's not other questions, let's move on to the next speaker. And thanks Stefanie again.
Thanks.